All right, so last time we ended up uh, formulating this problem that we were trying to solve. So we said that in order to find ux, the equation that we need to satisfy are these, and that should be satisfied at each and every point in the domain. And in addition to these conditions, what we also needed was this material constitutive law. So this was something that we were talking about last time, and I went through some of the theories and some of the general principles of uh, how to build material constitutive laws. So I think a couple of things that maybe I should mention again here is one thing about this material frame indifference. Now this, sometimes people confuse this with coordinate independence. But this material frame indifference is really a physical principle. It does not have anything to do with coordinate systems. So what this really means is that if there are two frames of reference, so if I'm looking at a material particle, somebody else floating around in space is looking at at a material particle, they both have their own frames of reference. Those frames of reference are not coordinate uh, coordinate systems. So there's a little bit of a difference, but let me not try to go into too much detail there. The main thing to remember here is that when one frame of reference, let's say somebody is rotating about and trying to observe the same thing, then that rotating frame of reference is not an inertial frame of reference. And even though it is not an inertial frame of reference, even then this constitutive material model that you develop must hold. So that's a little bit key there. Um, so we went over this theory about hyperelasticity, and what this really means. Whenever you hear the word hyperelastic, all that it means is that there exists this scalar energy energy function, not functional. Uh, what this means is that at every point you can express the strain energy stored in that at that point by a scalar function. Um, and I was telling you last time about all these different forms of scalar energy functionals, and we talked about this form where people try to express the strain energy function as in terms of invariance. Now, last time I think we were saying that the reason that we do this is so that it becomes coordinate independent. That is true, it becomes coordinate independent, but the more important reason is that as soon as you express uh, your strain energy in terms of the invariance, it also becomes isotropic. So ideally, people express the strain energy function for isotropic materials in terms of their their deformation invariance. So the reason is that these are just three scalars, 1, 2, and 3. They are just three scalars. As soon as you express your strain energy in terms of three scalars, you have just lost all information about directionality. So this is also an important point to keep in mind. And then we talked about this small strain Hooke's law. So this is something that hopefully you all are familiar with. And these lambda and mu are the two parameters that any linear elastic small strain material will have two material constants. And I showed you some of these relationships between the material constants last time. So given all these information, we said that how do we solve this problem? And essentially what we are trying to do is we are trying to solve this governing differential equation. And just to get an idea of how we could solve this kind of a problem in one dimensions, in three dimensions it is really not, it's very hard to come up with a closed form solution, an exact solution to that problem. So we took a look at this 1D problem. Um, this is a bar that is hanging from the ceiling, and we have applied some load to it, and we wrote out the governing differential equation, and we said to solve this, we can solve this. This is a one-dimensional problem. We can easily express, we can take b to the other side, and we can start integrating. So we can simply solve this with direct integration. And when you do that, this direct integration creates a couple of constants of integration. So those constants can be evaluated simply from your boundary conditions. So the two boundary conditions in this case we said were displacement at x is equal to 0 is 0, and traction at x is equal to L should be equal to P. And if you do that, you can calculate your two constants C1 and C2 and get your final solution in this form. So this is also a little bit of a hint to your homework 2, problem number 3. So let me briefly just describe that to you. So in this problem 3, I'm asking you to write a MATLAB program that will solve this one-dimensional problem. It is the exact same problem. But the only thing is that the user, that is me or whoever is using your program, should be able to enter any sort of body force function. Okay? And the way we do that is, there is this file sample1d.txt that I've also posted along with the homework. And if you go and take a look at that sample file, this is what it looks like. So L is the length of the bar, C is the Young's modulus, U0 is the specified displacement at x is equal to 0, and TL is the end displacement. So if you do this sample, and the body force, it's actually represented as a function of x. So how many of you are actually familiar with this sort of a notation in MATLAB? Okay, not very many. So this thing, the way that we write or create an inline function in MATLAB is using function handles. So whenever what this line is saying right here is that we are creating a function of x, and that function of x is equal to x multiplied with 10 minus x. So this is a quadratic function. I can create any other function I want in a similar way. So for example, if you take this function and if you run your code, let me see if I can. Okay, so it's asking me for the input file name, and I select this input file, and these are the two plots that are also attached along with your homework. I'm not sure. So this is the displacement profile, and you can see that I said that the displacement at x is equal to 0 should be 1. So that displacement is 1, and it increases because we are applying a body force and an end traction, so it increases, and the slope initially is much larger, then it becomes smaller, and it goes up like that. So in addition to that, we also have this stress plot. So you can see that the stress at x is equal to 0 is 260 something, and at x is equal to 10, which is at x is equal to L, the stress is equal to 100. Now this was the applied traction at our endpoint. So if you go back and take a look at this this input file, we said that traction at L should be equal to 100. So that's right here. Traction at L is equal to 100. So similarly, you can also try out different functions. So let's say if I choose something like 0, where is multiplied? Multiplied with x, and I'll let the other things remain there, and let me say that traction is equal to 100, and let's say the displacement is also displacement at x is equal to 0 is 1. So what is the solution to this problem? So what I'm saying is there is this bar, the body force is 0, I'm applying an end traction, which has the amount 100. So if I were to, what would be the solution of this? What does U look like? Yeah, the stress would be constant along the bar. What does that mean for the displacement? It should be linear. Displacement should be linear. So if I run this again, let's see if we get that. Okay, so this is the constant stress, constant value of 100, and this is the constant or the linear displacement. It starts out at 1 because I said that the bar has a unit displacement at the left end, and the displacement profile is then linear. Okay, so the same way you can also experiment with a lot of different types of body forces, and this program should be able to solve all these different types of problems. And I've already attached a template file, so really it's not a very long program. I think it's 5 or 6 lines and some fill in the blanks. So, but anyway, so so the way to think about this problem is as follows. So what we are really trying to solve is this equation, d cu prime. So let me call this homework 2 hint. So this is d cu prime dx is equal to minus b as a function of x. That was your body force. Now if I take my dx to the other side and start integrating, then I'm going to integrate from 0 to L, or actually let me not put the limits right now. This integral right here would become cu prime, and what we would have here is minus integral of bx dx plus c1. So what we are essentially saying is that if there is a bar and it has this body force bx, then the area under the curve, this area under the curve is this integral right here. Okay, and essentially what we are trying to find out by doing this integral is we are saying what is the function whose derivative would be equal to cu prime. So as you know that if you add some constant right here, this c1, so what you can do is you can take this curve and you can shift it by any amount. Its derivative would still be the same thing, right? So that's the sort of the physical interpretation of this c1. So if you look at the code, that template code that I gave you, essentially what I'm doing is I'm trying to find out the area under the curve of B, and then I'm going to reverse calculate C1, and that will give me the stress. And once you equate the stress at L to the given value, then you have found out C1. And if you integrate it again, you will get the displacement. So think about it a little bit, and hopefully it should be clear once you take a look at the code. So, all right. So starting with all these one-dimensional problems, we're going to take a look at, for the next maybe couple of next few lectures, we are going to take a look at these one-dimensional problems. And the reason we are doing that is because obviously these one-dimensional problems we can solve almost exactly every time, but we cannot do that for general two-dimensional, three-dimensional problems. And we are going to try to look at some techniques, and then we'll apply those techniques to the two-dimensional and three-dimensional problems. Okay, so here's the problem statement. Again, we are trying to solve this equation. This is div s plus b in one dimensions, and we have some body force, we have some end traction. At the left end, we also have some displacement boundary condition. So Now this form, this is a differential equation along with its boundary conditions. This form is called the strong form of the problem. And or sometimes people also just refer to it as governing differential equation. Governing because it governs the behavior of this problem. And also there's some references mentioned here if you want to take a look at some of the details in there. So now we just said that for 2 dimensions and 3 dimensions, this problem would be hard to solve. So we are going to try to formulate it in a different way. And one way to formulate that is using a method of weighted residuals. So let's try to look at what this means. So let's go to some point, any point along the length of the bar. And at that point, this equation has to hold. So one way to write that is, let's say, sigma prime plus b. This is a function of x. Now, if I take some variable u bar and multiply it with this quantity, and if I say to you that I have this quantity div s plus b in my hand, you give me any number and you multiply it with that number, this should turn out to be 0. If that happens, then you can definitely say that div s plus b is 0 at that x. Does that make sense? So what we're saying is, you give me any u prime, I will multiply that with this bracket quantity, and if the result is 0 for all u prime, then we can be sure that div s plus b is equal to 0 at that x. Okay. So in addition to that, we are going to integrate this over the length of the bar, and we are going to call this a functional g u u bar. And I'm going to say that this is a triple equal to usually means defined as. So I'm defining g as this quantity. Okay. So once again, if I now this u bar is a function of x, this bracketed quantity is also a function of x. If I say that this g must be equal to 0 for any function u bar, then you can be sure that this bracketed quantity div s plus b is going to be 0 at each point along the length of the bar. Okay, and this is the statement of this fundamental theorem of calculus. But before we get there, let me say that this is a functional. It's a little bit different from a function because the inputs that it takes are actually functions, and this is not u, this should be sigma. So this g is a functional of sigma and u bar. So what that means is that it takes in input 2 functions and it combines them in such a way that it produces a scalar. So a functional is a sort of a function of functions, and the output that it gives is a scalar. Okay. So in addition to this, we also have a couple of boundary conditions. So what we are going to do is actually we're going to take this quantity, and since this quantity is equal to 0, then if I change the sign of this from plus to minus, it would still be 0, right? And the reason I'm changing the sign from plus to minus is because this is just a convention. It doesn't affect your math or physics in this problem. So in addition to this, I'm going to add a couple more terms. We're going to say that u bar at 0 times t0 plus sigma 0. Now, and I'm going to add another term, u bar at L times TL minus sigma at L. So you should be able to see that this term is nothing but the Cauchy relationship that says tractions are sigma times um, sigma times the normal vector. That is, the traction at the point x is equal to 0 is equal to the stress at x is equal to 0 multiplied with the normal at x is equal to 0. So what is the normal at x is equal to 0? Pointing in the negative x direction, so minus 1. Normal, the normal vector is pointing at the negative x direction here. So this is the Cauchy relationship at x is equal to 0. And another way of expressing that is right here. This is the Cauchy relationship at x is equal to L. So the normal at that point is plus 1. Right? The normal at this point is in the positive x direction. The normal here is in negative x direction. And all I've done is added terms that should be 0. So now this is a functional of two functions, sigma and u bar. If I can show somehow that this functional is 0 for all u bar, then I know that the sigma that I used is the solution to my original problem. So this is a method of weighted residuals. All I did was I took this residual. If this is not equal to 0, it is called a residual. So we took the governing differential equation, we multiplied it with some function, and we said that if we can show that for all u bar this is 0, then our differential equation is satisfied. And this is pretty much the fundamental theorem of calculus of variations. So how many of you have seen this before? Okay, yeah, most of you have seen this before. So one of the things here is that the choice of u bar. We just said that we should be able to choose any u bar we want. But are there any restrictions on this u bar? So one restriction that this theorem poses on the types of functions that we can choose is that it should be square integrable. And let me tell you what that means is, so to understand why this function needs to be square integrable, does anybody remember the proof of this theorem of calculus of variations? Why can we say that if this quantity is true for all u bar, then sigma prime plus b should be equal to 0? If it is true for all u bar, then I might be able to choose any u bar I want, right? If I choose a u bar which is actually equal to this quantity, then that becomes sigma. Let me write that out. So if I choose u bar is equal to sigma prime plus b, then the integrand will become integral of sigma prime plus b squared dx. And let me for now leave out the boundary terms, but this integrand can be 0 only if, now this is a square of something, so this is if this integral will be 0 only if this quantity is 0 at each and every point along the x. And if you take a look at this, this is some function squared. So this theorem of calculus of variations actually depends upon the fact that this function should be square integrable. So any u prime or any u bar that we choose has to be square integrable. That's the reason for this. But what are all these different types of square integrable functions? Yes. Right, but I think maybe what you're missing here is that u prime can be anything. What the statement that we are making is that we have some quantity in our hand. You give me any u prime, all u primes. I will take that u prime, multiply it with this quantity, integrate it, and we should get a 0, no matter what u prime you give, u bar you give me. So if that statement holds, then we can say that our bracketed quantity, or this equation, is equal to 0. So in order to prove the theorem of calculus of variations, what we are saying is that if this statement is true for all u bar, then I might be able to choose any u bar I want. If I choose a particular u bar, then I can show that this squared quantity should also be 0. And this will be 0 only if this equation right here is satisfied.
Why did you choose U bar as only sum of pointers when you knew that there is a solution to the
So in order to prove the theorem of calculus of variations, we have to choose, this is one choice. The statement says that u prime multiplied with this quantity is equal to 0 for all u bar. So how do I prove this? If I want to prove that statement, then I can choose any u bar I want. I multiply it with the bracketed quantity, so it becomes a square. Now I know that this square and integral will be 0 only if this quantity is 0 at each and every point. And this is a subtle point, so you should really try to understand this. And maybe after the class also we can discuss a little bit if you are not sure. I don't think you. So yeah, so try to think about it, and if you there's a section in Jumsted's book about the proof of this theorem. So take a look at that also. There's a difference between any function u bar and all functions u bar. So you have to sort of understand that difference in here. So yeah, the restriction that we are going to pose on u bar is that it should be square integrable. And what that means is that if we evaluate this integral, it must exist, meaning that it should be finite. If we try to integrate that, it shouldn't go to infinity or blow up. All right, so some of the possible choices for these function spaces. So we also introduced this notation here. We are saying that if for some sigma this condition holds for all u bar, then we can say that sigma is the solution to our problem. And we are saying we are using this notation. This symbol is called the for all. So for all u bar, an element of some function spaces. So what this function space is nothing but just a collection of functions. So some examples of these functions I've given you here. You can see that there are functions which are actually discontinuous, and that is perfectly fine. Even if a function is discontinuous, you can still square it and integrate it. So it is still square integrable. But if you take this function and if you take the derivative of this function, then the derivative actually does not even exist at the point of discontinuity. And it can be shown that the derivative would be proportional to what is called a Dirac Delta function. For any discontinuous function, the derivative is proportional to a Dirac Delta function, and that function is not square integrable. So, so some of the function spaces that we can choose or people choose in finite elements. This is called the L2 space, and the reason it is called the L2 space is because if you give me a function, there is a norm. Norm means that some measure of how big that function is. This norm is called the L2 norm. So if this norm exists, then that function is belongs to the L2 space. It is also, this L2 space is also equivalent to another space which is a Hilbert space. So I'm not going to expect all of these functional analysis from you all, but if you read any finite element book, especially the book by Hughes, he will use those kinds of terminologies. So I think it's better for you to be familiar at least with what those spaces are. So if you take a function and you can square integrate it, then it belongs to an L2 space, or it is also called a H0 space. You could also take a function that is continuous. So these continuous functions are denoted with C0. 0 actually denotes the derivative of that function. So what we are saying is that the derivatives up to order 0 are continuous. So this continuous functions are a subset of square integrable functions, and this is apparent also from here. This function is discontinuous, but it is square integrable. The rest of the functions, they are also square integrable, but they are further more specific that they are also continuous. So this space, the space of continuous functions, is a subset of square integrable functions. And if you take the derivative of a function, the first derivative, and that derivative is also square integrable, then we call that this is an H1 space. And the reason that we care about derivatives is because if you see all our differential equations, they are, Cu prime, another prime. So we are going to be taking derivatives of our functions. That's why we care about what order derivatives are square integrable, what order derivatives are continuous. And actually in beams and plates, we have fourth order derivatives. So in those cases, we will care about C2 continuity for our shape functions. But anyway, we'll get there when we get there. So this is just a nomenclature of how people choose these spaces that these functions can belong to. So yeah, I've already mentioned this. If you have a discontinuous function, its derivative is the Dirac Delta function, which is not a square integrable function. So if you choose, if you are trying to approximate a solution, this would not be a good choice. Okay, so now this method of weighted residuals that we just talked about, all that we did here was we took this equation div s plus b and we multiplied it with a u bar and we integrated it. So if we start that way, we can also show that this method of weighted residuals is equivalent to a principle of virtual work. So for those of you who did not even take 570, the principle of virtual work is something that you might have taken in structural analysis, and it's the same principle of virtual work. So the way we start here is the exact same way. We're going to take our differential equation that says div s plus b, and in general, if anybody gives you any differential equation, take that differential equation, multiply it with a u bar, and integrate by parts. That's a standard procedure for all finite element formulations. So we take this div s plus b, multiply it with u bar, and now we are going to do integration by parts. So if we integrate this by parts, the first term is going to lead us to that we'll transfer the derivative from sigma over to u bar, and this is the term that we get. And plus we will get some boundary term. So that boundary term is nothing but this. Are you able to see that if you do the integration by parts for this term, this is what you will get? Okay. And then the remaining term that we have is minus u bar times b, and that's written right here. So let me expand this boundary term, and if you write this out at L, so there's a minus sign that goes here, minus at 0. Okay, and if you take a look at the original G that we defined, that original G had another couple more terms. There was this term, and we should add that term to this functional. So if we write out minus u bar at L times TL minus sigma L, and minus u bar at 0 sigma 0 plus T0. So this is the exact same functional that we had before from weighted residuals. And if you look at these terms that came out from the boundary, these terms actually exactly cancel off with this term and this term and this cancel off. So if you cancel off those terms, what you're left with is this first term right here, and this is nothing but the internal virtual work. If you have a body that is in equilibrium, if you take small variations of that, the internal virtual work is going to be given by this. And similarly, you have other terms that are going to be the external virtual work. So this body force, that's an external force, multiplied with the virtual displacement, and similarly this traction at L and traction at 0. They're all external forces. Multiplied with the virtual displacement there, what you get is that this is the external virtual work term. So this is essentially the principle of virtual work that says that the internal virtual work done should be equal to the external virtual work. And if you can satisfy that for some sigma and for all u bar, then we know that this equation is satisfied, that div s plus b is satisfied. So another thing to note here is that we started out with this equation. We took div s plus b and we did our integration by parts, and out came two boundary terms. Those two boundary terms naturally cancelled off with some of the boundary terms that we already had. That's why these are called natural boundary conditions. And if you take a look at this entire functional, the displacement boundary condition that said u at 0 should be equal to some value, that's not even here. So that's why the other boundary condition that's on displacement is called an essential boundary condition. Okay. So in this equation now, the unknowns that we have to still solve for are the stress sigma, and now there is also this unknown traction at 0, because what we are trying to solve is this equation or this problem. We know the traction at L, but we don't know the traction at 0. We know the displacement at 0. So one way to actually get rid of this unknown is to choose that we will choose u bar at 0 to be equal to 0. And this is a choice. You don't have to do that. Okay. So if you make that choice, then our virtual work functional that remains can be stated as this. This is nothing but the principle of virtual work. We say that if for some sigma this is equal, this condition is satisfied, then div s plus b is equal to 0 and we have equilibrium. And further the tractions at the right end are also equal to this quantity. So another thing to note here is that by itself, the principle of virtual work, we never mentioned u at 0. So what we are going to do is we are going to say that our u bar, that must satisfy h10. So what that means is, if you go back to the previous page, this h1 space was the space of functions which have first order derivatives that are square integrable. And this is the reason this is important is because in this case right here, we are trying to calculate u bar prime, and sigma is also going to be proportional to u prime. So u bar is a virtual displacement, the real displacement is u. So we need to calculate both derivatives. So in order for this integral to be well defined, the u bar function has to be in the space h1. And this 0 at the bottom, this denotes that it should satisfy this condition. Now this condition is a little bit different from the essential boundary condition. The essential boundary condition was that u, the real displacement at 0, should be equal to some value. We are not saying that this value is 0. So the difference here is that the real displacement is equal to some value at the left end, but the virtual displacement has to be 0 at the left end. And the reason that we said that it has to be 0 is because we wanted to eliminate this term. And we don't lose anything by eliminating this term. Once we calculate our sigma, we can go back and actually calculate the traction from whatever solution we get. So this is all just some sort of a algebraic manipulation of our equation. So all this that we are doing is only so that we can put this this equation in an integral form, so that we can then get approximate solutions. So once you get this, once you go over this derivation, once you get this derivation, how it is done, this derivation or this procedure is going to be repeated again and again for any finite element formulation. So all right, so all this while we also said that we are going to work with this sigma and u bar. We never introduced the material model, right? This sigma was related to the equation of equilibrium. It does not have anything to do with material model. But now if we choose a particular material model, let's say the Hooke's law in one dimension, then the modified functional, now it's a function of u and u bar, not of sigma and u bar. So this modified functional is again can be written as the internal virtual work minus the external virtual work. And if this is 0, then we know that equilibrium holds. So this is all just trying to express it in a different form. So finally we can state the problem in this way. We started out with the strong form right here. This was the governing differential equation and boundary conditions. We did some algebraic manipulations, and we end up now with this equation. We're saying that the problem is find a function u, where u is the real displacement. This function u has to be in the space h1, 0, meaning that if you take the derivative of u, that derivative has to be square integrable. And further, we are going to restrict that the real displacement must follow the essential boundary conditions. So this is the essential boundary condition at x is equal to 0. So find a function u that is h1, meaning first derivative square integrable, that also satisfies the essential boundary condition, such that this functional is 0 for all u bar. And this for all statement is very important. You cannot say that here are a couple of u bars and my functional is 0 for these couple of u bars, and therefore I've solved the problem. You have to show that this functional is 0 for all u bar which belong to, again, the h1 space, but in addition they have to be 0 at x is equal to 0. So if you can find such a u, then you can say that you have solved the problem, that your equilibrium holds. And this statement is called the weak form of the same problem. So earlier, that governing differential equation, this was called the strong form. This is called the weak form. And sometimes people get confused that strong form is really strong, and weak is somehow not an approximate measure, an approximate way of solving. But the important thing is that if your u bar function is differentiable, then strong form and weak form are exactly equal. There is no approximation up until this point. Okay. So the next step is really the approximation. In your books, you might actually see a couple of alternative notations. So I included some of those here. The Hughes book likes to express it in terms of what are called bilinear forms. So they define a quantity A, which is nothing but your internal virtual work. And this bilinear form is from the Reddy book. So if you see these alternative notation, they're just saying the exact same thing. This form is also a bilinear form, and this is defined as the load term. And so the alternative forms for the same functional are, this is from the Hughes book, this is from Reddy's book, and this is from Jelmsted's book. So all these forms are pretty much exactly equivalent. So when you're taking a look at those things, you don't need to be too confused about all this. All right, so we just said that we have the strong form and we have the weak form. But the weak form itself, if you go back and take a look at this weak form, we are saying that it has to hold for all u bar in this space. So this is again, we have just transformed our problem from one infinite dimensional problem to another infinite dimensional problem. So it would seem like that we haven't done anything. But the trick here is due to the Ritz method. So what Ritz said is that I can find out approximate solutions to this weak form by assuming that my solution is going to follow certain patterns. So if I say that I'm going to build my function, the solution u, as a linear combination of some known functions. Okay. So what we are saying is, let's say we choose h1, h2, h3, h4, and so on. All these functions are known functions, whatever function you want. You want polynomials, trigonometric, whatever. But let's choose these functions and let's express our unknown solution as a linear combination of all these functions. So all that we have boiled down our infinite dimensional problem to a finite dimensional problem where all that we are trying to find is these scalars A. So you can express this in this manner. So if let's say we have n functions, so we will write this in a matrix form. These are all unknown scalars. These all are known functions. So now you can imagine that this is a very big restriction on the original space that we said. In the original space we said any function that is square integrable, we must show that our g should be 0 for those functions. But here we are saying that we will only consider functions of these types. If we can somehow show that for functions of these types, that g, the virtual work functional is 0, then we are still good, because I mean you can consider this all these functions. If you try to take linear combinations of this will still span quite a lot of space, right? So the couple of things that we have to restrict all these functions again is that this function h should be smooth enough. What that means is again that its derivative has to be square integrable. And if it is complete means that if you choose enough number of these functions, then your final solution will approach the exact solution. So another thing here is that all these functions hi, they are all starting from 0. Okay, and we are going to add this special function h0 that will take care of the essential boundary condition. So I can add any function h0 as long as its value at 0 is equal to the specified displacement. And everything else starts from 0. So if we do that, then we can express this solution in this form. So we have reduced from an infinite dimensional problem to a very manageable problem. But of course, we have lost a lot of information. We have made a huge approximation. So depending upon how well you choose all these functions, your approximation might still be very good. So, all right, so yeah, this is the note that I just told you, that the essential boundary condition is satisfied by this H0. And some of the examples are here. Let me just briefly mention that there is this Galerkin approximation. So we just chose the space for the solution. We haven't chosen anything for the virtual displacement. So Galerkin came up with this idea that, well, we are choosing all these approximation functions for our solution. Why not use the same functions for our virtual space also? So if we make that choice, then this is called a Galerkin approximation. And so if you do that, then this is the sort of approximation that you get for the virtual spaces. And you can plug that back into your weak form. And ultimately, if you go through the algebra, what you will get is the familiar equation that this G prime should be equal to 0, and that will be valid for all virtual displacements if the bracketed quantity is 0. So this is the standard procedure for all finite element formulations. So we'll go over this last part again next time on Wednesday. And let me know if you guys have any questions. All right, see you on Wednesday.